the open mapping theorem, B dash Banach spaces T map from B to B dash T linear continuous and onto. Then rather let's say that this is, it's a word theorem, so let's write theorem over here. Then T is an open map in the sense that, okay, so this is what we want to prove. Just a note on this thing. So what does this mean? T is given to be onto, so every element here has a pre-image. The map is linear. T of x plus y is T of x plus T of y, and T of alpha x is alpha times T of x for all x, y in B and for all scalars. Okay. And T is also going to be continuous. So if you take any U which is open set in B with respect to the metric topology on B, then what does this says? This says that T of U is an open set in B dash. So image of open set is open. The topological definition of continuity is that inverse image of open set is open. If the map is on 2, then what it is, this is guaranteed between two Banach spaces. If the map is linear and continuous as well, then image of open set is open set. So if T is also given to be 1, 1, 1, 2 and T is linear and continuous, a corollary of this thing would be what? T is in fact a homeomorphism. So the inverse is also continuous because inverse image of open set is open of the inverse map. So let's try to prove this thing. To proof, let U be an open set in B. Okay. So T of U is a subset of B dash right hand side. Let Y belong to T of U. So there exists X belonging to B, or rather X belonging to U, which is a subset of B, such that T of X is equal to Y. Since X belongs to U, U open in B, this implies that there exists a ball centered at X with radius R. So ball with respect to the metric of B which is contained in what? U. So this ball, let's call B with respect to this B, capital B. So I'm using, so let's use the small b symbol so that things are easy to understand. So rather this ball can be written as, so SR we know that. What is SR? It's a ball centered at 0 with radius R. Collection of all those U such that norm of U strictly less than R. So SR is a subset of B, unit ball with radius R. This object is nothing but X plus SR. Is your this small b, this one. The translation property. So what do we get from here? So if you take the image of this T, so let's focus on this SR. It's a unit ball centered at 0 with radius R, open unit ball. So T of SR is the image of the unit ball centered at what? bro, with radius r. Okay. Now, by the previous proposition, what do we have? That 0 is an interior point. So 0 by previous proposition, we have that 0 is an interior point. The 0 is an interior point of TSR. So what do we get? We get that. So if you look at y plus TSR, so y plus 0, so y is an interior point of this set. Interior point of this set. But what is y? Y is t of x. So t of x plus TSR, which is nothing but t of x plus SR. So y is an interior point of this set. Now, if you look at this object, t of x plus TSR, t of SR is contained in what? This is in fact y, and t of SR, this is the same thing as this thing. So this is an object, t. This set is contained in t of u, because this is the ball centered at 0 with radius r. This is y. So this is nothing but the image of the ball centered at y, centered at image of centered at x, t of x. Okay. So image of, so if you take that x and SR and so on, so this is in fact contained in t of u. Okay. But t of u, so what we have that because y is an interior point of this set, so what happens? 0 is an interior point of TSR, y is an interior point of this thing. Here itself, the argument could be done the following way. So let's erase this part, system. So I'll use this fact, because 0 is an interior point of TSR. So there exists what, by definition of open set, there exists a ball SR dash, maybe say, let's say, so this is the SR is used here. So there exists a S, maybe say L. There exists a SL dash of B dash. This is the ball centered at 0 with some radius L greater than 0, such that SL dash would be contained in what? This is a unit ball in B dash. Not unit ball, a ball of radius L centered at 0. So SL dash is contained in what? Is contained in SL dash is contained in TSR. Okay. And then y plus TSR, what would happen to y plus TSR? Y plus TSR would be nothing but add y on both sides. If you add y on both sides, what do you have? Y plus SL dash is contained in y plus TSR. Okay, but what is y plus TSR? This is in fact this thing. This is contained, as we have already written here, this is contained in t of u. In other words, y plus SL dash is nothing but a ball centered at y with radius L, which is completely contained in t of u. So what we have got? We have shown that if y was any point in t of u, we have found out a ball centered around that y. That ball is completely contained in what? T of u. And hence what we have shown is that t of u is in fact an open set. Y was any arbitrary point. So this proves the open mapping theorem. So what we have seen is the projections in linear algebra. Projections. Okay. So, or rather algebraic projection. So what is an algebraic projection? Suppose P is a map from V to V. So V is given to be a vector space over a field F. So P, if P is a linear map and P square is equal to P, that is P of X. So what does this symbol P of X? For all X in V, so linearity, the first condition, the second condition is this thing. Then we say that P is in fact a projection. What kind of projection? It's an algebraic projection. Now let's look at the image space and the kernel of this linear map. So P of X plus Y, P of X plus P of Y, P of alpha X is alpha P of X. This is the condition of linearity, and P of X is P of X. This is true for all X and Y belonging to V, all alpha belonging to the field F. Okay. So let's look at the range or the image space. The image of P is what set? It's a collection of all those U belonging to V such that U is equal to P of W for some W belonging to V. So this is the image space. So every element, those elements which have pre-image, image of P. So the kernel of P or the null space. The kernel of P is collection of all, maybe say, we'll use the notation, all those X such that P of X is equal to 0. This is the image of P, this is the kernel of P. Let's observe the following fact. Since P is a linear map, P of 0 is equal to 0. So the pre-image of 0 is 0. In other words, 0 belongs to, these are, as a fact, these are the subspaces of V. So 0 belongs to the image of P also, and 0 belongs to the kernel also. Let's take an object which is in this set. If U belongs to image of P, this implies that P of U, U is equal to some P of W. There exists a W belonging to V. Apply P on both sides. So P of W is what? P of U. This is nothing but P square of W, which is P of U. But what is P square? P square is given to be P of W, and that is P of U on the right hand side. This is by using the definition of idempotent, that P is idempotent. So P as idempotent. But what is P of W? P of W is nothing but from here is in fact U. So what we have got? We have got from here is that U is equal to P of U. So we started with an object in image of P. What we have got is that if you take the image of that element, that is again U. Conversely, if you have any other element which satisfies this condition, U is equal to P of U, then what happens? Apply P on both sides. So what do we get? So if you apply P on both sides, is P square of U. But P square is given to be P. But that is P of U. So P of U is what? P of U is W. So P of U, what we want to show is that in fact every element here, okay, just a minute, we'll write more clearly. Drop this below part. So any u is there in image of P satisfies this thing. Conversely, let x belongs to V such that x is equal to P of x. That implies that x belongs to the image of P. So x is equal to P of x. Okay. And that is clearly, if we have x is equal to P of x, that is in the image set. Okay. And if we apply again what? P, that is no issue. So P of x would be what? P of x would be P square of x. Just a side note. So the point is that if you have an object in the image set, then there is a unique relationship which is observed here, which is the object on the codomain. Here it is the image. So image of the element, it's the image itself. And conversely, if an element is there, that is also in the image. That's trivially, as you can see, x is equal to P of x, that is in the image set. But every element here, u was any typical element, we are able to show that u is in fact P of u. So what you can say is that the point is that the image of P is in fact the kernel of I minus P, because this condition over here could be written as I minus P, send u on P of u on the left hand side to u, so you get this thing on u. So u belongs to the kernel of this map. We'll show that this is also linear map. If P is linear, this is linear. Okay. And conversely, if you have the kernel of P, let's look at what happens to the image set. So image of P we are able to show. So this is the case. Let's look at the kernel of P. Collection of all those x such that P of x is 0. Okay. So if you have the kernel of P, okay, that P of x is 0, what do we get from here? What is image of P? What we want to show. So let's look at the image of I minus P, the set. This would be the collection of all maybe say small h such that h is equal to some I minus P of R or some R belonging to V. This is all h belonging to V itself. The point is that this is the definition of image of I minus P. A typical element over here, P of x is 0, we want to show that it is image. Okay. So what do we get? Take a typical element over here. So x belongs to kernel of P. So P of x is what? P of x is 0. So we have to show that that element is in fact here also. So if you consider the element x minus P of x, let's look at the element x minus P of x. Let's call this thing as h, or rather let's call this thing as r. Then what do we get? If you call this element as r, then P of r, P of x minus P of x, this is P of r. But this is nothing but P of x, because of the linearity of the P, minus P square of x, which is P of r. But P is given to be what? It's an algebraic projection. So what do we have? We have that P square is P. This is nothing but P of x minus P of x. This is equal to what? 0. Okay. And Hence, what do we have? This is 0, so this is 0, so P of R, this is 0, so R belongs to what? R belongs to the, so R is in fact the image of what? So R belongs to the kernel of P, okay? Not only that, R is in fact I minus P of X, okay? Over here is that what is the value? If you have this object x minus p of x is already 0. So in fact r is equal to, from here r is equal to x. So what we can get, x is equal to r. Substitute here. So what we have got, x is equal to I minus p of x. So in fact x is a typical object. So x is in fact the image of, x is in fact in the image of I minus p, and so on. Conversely, if you take any typical element over here, which is what in here, it is in fact in the kernel of P. So let's try to prove that also. So H is I minus P of R. Apply P on both sides. So P of H is P of R minus P of R, which is nothing but P of R minus P of R, which is in fact P of R. And since P square, P is what map with this map, so P square is equal to P. So it's an algebraic projection, so P square, so we'll be using the idempotent property, P square is equal to P over here. So we get this thing, this is 0. So P of H is equal to what? This implies that H belongs to the kernel of P. So it was typical element over here, so we have shown in this way also and this way also. So in fact what we have shown is that the following. So the kernel of P is in fact the image of I minus P, and the image of P is the kernel of I minus P. What one needs to show is that I minus P is indeed, if P is given to be linear and idempotent. So let's check that first idempotent property. Given that P square is equal to P, what does this imply? So let's square this thing, I minus P on I minus P of X. So with this we get that I minus P of X minus P of X, and applying on this thing we get X minus P of X, I on this thing minus P on this thing, so it would be Px plus P square X, but P square is P. So what does this imply? X minus P of X minus P of X plus P of X. This cancels, this cancels, this is X minus P of X. So X minus P of X, this object over here is nothing but what? X minus P of X is I minus P of X, X minus P of X. But this was what? I minus P of I minus P of X. So this implies that I minus P whole square is I minus P. In fact, this is also an idempotent operator. Okay. Not only it's an idempotent operator, it is in fact a linear operator also. Let's show that if given P is a linear, I minus P is also linear. So given P as what operator? As a linear, then I minus P, we show that P is a linear operator. So let's take any two element X and Y belonging to V, then X plus Y. So first condition of the linearity, so Px plus Y, P of X plus Y is Px plus P of Y. So let's apply this thing on I minus P on X plus Y, which is nothing but X plus Y, I of this thing minus P of x plus y, which is this thing what, x plus y minus px minus P of y. What do you get? This is x minus P of x plus y minus P of y. You get x minus P of x, y minus P of y. So, which is nothing but I minus P of x plus I minus P of y. What do we have? So, this we have the condition for at least the first part. Let's take alpha is any scalar. Then what do we get? If I is any scalar, then if alpha belonging to f, x is belonging to v, any, then I minus p of alpha x would be what? Alpha x, I of this thing, minus p of alpha x, which is nothing but alpha x minus alpha times p of x. So what comes outside? Alpha into x minus p of x. This is nothing but alpha times I of x minus p of x, which is nothing but alpha times I minus p of x, which is what? I minus p of x, of alpha x rather. This is the second property. So we have shown that I minus p is in fact a what map? It's a linear map. Now it's a projection. So what do you mean by projection? It is getting onto projection onto something. So what is that something? So let's look at the following object. Because the kernel of P is image of I minus P, the image of P is the kernel of I minus P. So if you have image of P, which is the kernel of I minus P, so this is nothing but collection of all, if this is U is there, set as U belonging to V such that U is equal to some P of W for some W belonging to V, then this is the case is that what can be done over here is that this set is the same thing as we have seen that U is equal to P of U. It's a collection. It's a collection of all those, we can write all those U belonging to V. U is in fact P of U. This is precisely this set. Okay. And the kernel is can be said similarly because the kernel of P is in fact the image of I minus P. So you have collection of all those X such that P of X is equal to 0. This set is there, which is the same thing as what? As an image set, if we have, this is collection of all those X belonging to V such that X is equal to I minus P of X. I can easily see that XX is there, XX cancels, PX is 0, minus PX is 0. It's precisely this thing. So this property is we can use this definition and so on. So what does this do? So this is a projection onto an image space. So P is a projection. So there is P is a projection onto image. U is equal to P of U. So in fact, if P is a projection, so we have two spaces, image of P, kernel of P. If P is projection, I minus P is also projection. So if P is linear, P square is equal to P property idempotent on V, then you have two spaces, image of P and the kernel of P. So later we'll see that in fact we require this to be a closed subspace. So the continuity of P is also required in Banach spaces and the Dirac sum and so on. So P is a projection onto what space? Onto the image space. So if you take any Z, then P of Z, Z is projected onto P of Z. So all objects are projected because, and the other object would be what? In the kernel. So the direct sum of image of P plus kernel of P, the direct sum of P, it may not be the whole space. We want to break down the whole space as the sum of image of P and kernel of P. So for example, if we take an object over here and object over here, so if you take any U belonging to image of P, U is what? P of U. The kernel of P is there, then what is given? If you take any X belonging to over here, P of X is what? Given to be 0. So if you look at, or rather let's write this thing as 0 is equal to P of X. If you look at this equation at the LHS and the U plus 0 is in fact PU plus P of X. PU, so which is nothing but P of U plus X. This is what? U. So the point is that what do we have is that any object and so if you take even U plus X also, so what happens to U plus X? Alternatively, if you take U plus X and apply P to this thing, this is nothing but P of U plus P of X. But what is P of X? P of X is 0, which is nothing but P of U. So P of U plus X is P of U. So we can write over here at least this is P of U. So if you take an object in the image space and the kernel, you add them. So we are getting U is equal to P of U. It's a projection onto the image space, the projection map P, and all the objects on in the kernel space. If you take any object here and you project it, if it is in the image space, then the image of the element of the kernel is 0. So if you add an element of the image and the kernel, it's again the image of this thing. So in fact, if you take any Z plus X, this is a trivial property. So what we will see is that later is that we require P to be continuous when we are dealing with Banach spaces, continuous. So these are the algebraic projection. So this gives two spaces M and N. M can be called as, let's call this thing by a name as M, and this as name as N. M is the subspace, N is the subspace, image space. M is the image of P. In fact, M is the kernel of I minus P, and N is in fact the image of I minus P. So I minus P is a projection on. So let's write that also. So P is projection on image of P set, and I minus P is projection on the kernel of P, okay, which is the same thing as the image of I minus P, which is the same thing as kernel of I minus P. The point is that what we have over here is the following, is that M is the kernel of I minus P is in fact the image of P, and N is in fact the image of I minus P is in fact the kernel of P.